Hi everybody and welcome to a tutorial on SkyCiv. Today we're going to take you through how to build a Boomilever structure using SkyCiv Structural 3D for the Science Olympiad competition. We're partnered with Science Olympiad to bring software to the students. So if you are part of a Science Olympiad team, you can purchase the software for $40 for 6 months. And today's tutorial is going to take you through how to build your model, so you can test the structure before you go ahead and build it. So you can test different designs and experiment with your designs before you actually go ahead and build them. And we're going to do that using software before we go ahead and build it, to make sure that the structure will hold under the loads that we've applied to it, and then we can go ahead and build it. So I'm going to start with a new file, so I'm just going to hit File, New, and we're going to be following a tutorial that we've written, which is available at skyciv.com, and it basically takes you through the step-by-step guide of how to build this model that we're going to work on. And so the first step is, well, we need to model something. We need to design the structure, and we start that by adding in nodes, and nodes are going to be the start and end point of all of our members. And so if I just click nodes here on the left menu, you'll see it's asking me to add a new node, and I'm entering in the X, Y, Z coordinates. And these are the X, Y, Z coordinates with reference to this global axis here. So if I click and drag, it will rotate, and I can see we've got X, Y, and Z. So if I put a node at the origin, which is 0, 0, 0, we'll see a node shows there. And I'll build it out in the X direction, which is that way. And so we'll build something that's about 0.5 meter long. So I'm going to put 0.5, which is 50 centimeters. And you can see that node has been added in line with the first node at the origin, and if I hover over it, it'll show me that it's 0.500. Now, before we go into the modeling, I'm also going to check my unit system. So just by going to settings, I want to make sure that all my units are in something that makes sense and are relevant to the structure that I'm building. So I'm building in centimeters. I'm going to just leave length as meters. So 10 centimeters would be 0.1 of a meter. So it's an easy enough conversion to make. But I want to make sure my material strength is in MPa, my density is in kilograms per meter cubed, force in kilograms, and pressures are both, pressure and stress are both in MPa. These are going to make things a lot easier for me moving forward, and with things like materials, we've provided some material table, and that's in the correct unit system there. So I'm going to build this model with reference to my length being in meters, so everything is going to be based off that. Now there's two ways you can build your model. One is to manually add the nodes like I was doing, and then join them just by clicking and dragging from node to node. But there's also a nice convenient pen tool here on the right. So if you open up that and click the pen tool, you'll be able to model out your structure just by clicking and dragging between nodes, and it'll pick up global axes like your Y axis or your X or your Z. And I'm also going to just change my snapping option to be a little bit smaller, so I'm going to do them in increments of 10 centimeters or 0.1 meters. And I'm just going to start clicking through to design my model. So I'll probably do something maybe about 30 centimeters wide. And we'll continue across that 0.5 meter span. And you can see it's going to pick up axes that, lined up with other nodes. And I'll just put a sort of midpoint to midpoint truss structure. Takes a bit of practice to hit the nodes right with the pen tool. And then I'm going to just build out a little bit this way as well to make room for where we're going to actually load the structure. You can also turn off the pen tool, so I'm going to create some anchor points. I'm just going to turn off the connecting members, so it's just going to now, if I click and drag, it'll just build up a node there, and I'm going to do that at 0.4 of a meter, and this side the same, 0.4 of a meter. And then I'll go back to connecting my members and connect 8 to 4 and 9 to 2. So you can start to see that the structure is taking form. You can see I've got some anchor points up there and a little bit of a truss structure to support the load that we're going to apply here. So you can imagine this is where your piece of plywood base would be. So I've got my nodes, my members. The next thing I want to do is add some supports here. So obviously we're going to anchor this to some sort of wall, and we're going to do that at nodes 8, 9, 1 and 3. So I'm going to add supports there. So to do that, I'll just click supports, and then I'm going to enter in those node IDs that I was just mentioning. So 8, 9, 3 and 1. And I'm going to make them a pin support. And the reason I'm doing that is because there's going to be some rotation available at those points. And so I'll just hit apply. So now my structure is held against a wall, so there's some sort of rigidity to it, and the structure is going to be rigid or held up against something. So it's not just going to, if I put a force here and nothing's holding it, the whole structure is just going to fall. But now we've got something that's holding it to something rigid like a wall. And so the next step would be, now that we've got our model, we've got it constrained, or we've got it supported, now we want to apply some loads. And we're going to do that just on this end. So we're going to simulate the weight effects of the sand. And we're going to do that, I'm going to apply a 4 kilogram load, but I'm going to separate that into 4 point loads, and I'm going to apply them each here. So that's just an easy way. There's a few different ways you can apply loads, but this is just a nice easy way that you can distribute the loads to those nodes. And so I'm going to go under point load, and I'm going to add to nodes 4, 6, 7, 2, and you can see they're highlighting there, so I can make sure that I'm applying the loads to the right nodes. And we're going to apply a 1 kilogram load to each of these nodes. Now, an important thing to note here is we're referring this in the XYZ magnitude. So we're looking at Y here, and Y is pointing up. So what I want to do is put a negative 1 kilogram load there. So it will be negative in the Y, which means there will be a down force in the Y. And if I hit apply, we'll see the 4 forces there, and you can see that there's an arrow pointing in the direction. So if you do get the direction wrong, you can just put a negative to flip it, but you will see that the forces are all pointing downwards, which is obviously the right direction that you want to apply these loads. Okay, so the last thing I want to do in applying loads is just, I'll go back and switch on my self-weight. So self-weight's going to include the effects of the weight of each of these members. So obviously the wood has some weight to it, and that applies load to the structure as well. So I'm just going to turn those on to include those in the analysis. So I've modeled up my structure, so I've added all the members that I want to include. I've supported it here at the base, or the piece of plywood, and then I've applied some loads and turned on my self-weight. So we've got some forces acting on the structure. So I'm going to just refer back to my blog piece, and the next step would be to add the balsa wood. So this software obviously requires you to input information about what the actual structure is made of. We haven't yet told it whether it's made of steel, concrete, and in this case it's wood. So we want to go ahead and add that material, or those material properties. And I'm going to be working off American balsa wood. So I'll just enter in American balsa wood, and we're going to put in a custom material here. And I'm just going to take that from the blog piece. So it's got all the properties here. So the density is 130 kilograms per meter cubed. 130. The Young's modulus is 3000 MPa. And I'm just checking my units to make sure that I'm adding them in correctly. The Poisson's ratio is 0.23. And I'm going to leave the yield strength and ultimate strength for now, and I'll apply those. So we should find that our material is now in our menu as American balsa wood. So that was quite an easy step. The next one is to add the section. So adding sections is a really important part of the design, because you're actually telling the software what size these members are. Right now they're just vectors in space, but we need to apply some cross sections to them so that they know how thick they are and how wide they are. Otherwise it's just a line. So to do that, we're going to go and add sections. And we're going to actually, we're going to do 2 types of sections here. So we're going to make these 2 members a little bit stronger. So I can click them and change the section ID to 2. And you see it changes color. So what this is telling the software is that there's 2 types of sections here. There's a black section, I can see section 1, and then section 2, which is green. And we're going to make these ones a little wider. We're going to make them 10 by 10 millimeters. And these ones we're going to make 5 by 5 millimeters. So to do that, we're going to now define what these sections are. So you can see they're not defined. So I'll click the black section, and I'm going to open up our builder here. And I'll open up rectangular. So I'm just going to add a rectangular shape. And you can see material here is structural steel. Obviously we want to change that to the balsa wood that we've just added. And then dimensions in millimeters, we're going to do these ones are going to be 5 by 5. And I'll go ahead and submit that. And you can see that the black section has updated itself as being a 5 by 5 rectangular shape or square shape. And then the green ones we're going to now add to the builder as well. And we're going to make these 10 by 10. And again, changing the material to the balsa wood. So what this is telling the software is that line has this cross section as a square. And that's been updated as well. So we have 2 cross sections now. Obviously these ones are a lot stronger, being a much larger section. And then we've got the smaller ones here in the truss. And we can check these, the input has been added correctly. This is a great time to check it once you've added your sections. Well, let's review the 3D renderer and make sure that what we've built is actually in proportion and makes sense. And that looks pretty good. And so I can go back to the wireframe and continue our testing. So at this point, I've added the supports, the model, created the model, added the sections and the point loads, and I'm ready to solve and get some results. So you will notice in the blog piece, adding loads is the 4th step, but I've just done that prior. So the 5th step is to review the results. And what we're looking for here is that the stress on a member will not exceed the material strength. So if we go back up to the properties, we've got some compressive strength here. So this is the stress or the pressure that causes the material to fail. So if we exceed these sorts of pressures in the structure, it means our Boomilever is likely to fail. So I'm going to take a conservative approach, and I'm going to use 7 MPa as my limit. So if anything goes over 7 MPa, I'm going to deem the structure as failed. And so we're going to go back into our model, and we're going to hit solve, and this is going to show all these results. So I'll leave it on the default load combination, and I'll go to stress. Actually, before I go to stress, I'll just check displacement. Displacement can be a pretty quick indicator that the structure is failing. And what it is it's showing you how much the structure and in what shape the structure is bending. So if I apply loads, I can see how it's bending there, and I can use this scale here just to animate it. But I can see the deflection is about 200 millimeters, which for a span of about 500 millimeters, 50 millimeters, that's quite a large deflection. So I can already sort of tell that this is probably not going to pass my stress test, but let's go through and check it anyway. So I'll go to stress, and what we have is a few different types of stresses that we want to check for. But what we're going to use is this right menu here, and there's a limit state that we can apply. So what this limit state is, I'm determining what limit I want to apply to the structure. So if I put 7 MPa, it's going to highlight any stresses that are above 7 MPa, and I can see there's quite a lot. So they've shown in red that the 2 upper members are failing, and then quite a few of these members in the truss structure are failing as well. Another quick check I can do is just checking the max and mins, and I can see I have a 95 or roughly 95 MPa stress, which looks like these ones, and that's obviously well beyond the 7 MPa limit that I've set for this structure. And I can check the other types of stresses to see if they're failing, and I can see it's failing in what kind of areas. It seems to be the bending stress that's causing it to fail. So the great part is that I've been able to determine this within a couple of minutes using the software rather than going out and building this design and watching it fail under the load. So it enables me to test these designs that we have, or the experiment with some of the designs that we come up with before we actually go ahead and build them. So what I can do now is just go back to the model and let's make some changes and see if we can get this structure to solve. Okay, so obviously we need to make some changes to our model if we want it to support these 4 kilos forces that we've applied to it. So let's make some changes to the model. And we're going to start with these 2 long members. So if I click member 10, it'll show me that node A, which is 8, is connected to node B, which is 4. So let's change node B to 6 and let's extend out how far these members support structure. So we're going to go 9 to 2, we're going to go 9 to 7. And let's also increase the strength of this truss structure. So we're going to delete these 2 as well as this node. And I'm going to highlight members 1 and 3. And you can see if I hold control, there's little shortcuts like that if I hold control and click and highlight, I can highlight multiple members and make changes to multiple members at once. And we're going to right click them and hit split members. And we're going to divide them into 3 parts. Oops. So we can see it's divided, added some nodes and divided each of those members into 3. And then we're going to build let's increase the strength just by clicking and dragging between the nodes. Let's create some cross members just to create some bracing in this truss structure. And that'll add more rigidity to it. So just keep clicking through. And the last one. And finally, we'll create some members between these stronger members, 10 and 11, and down to the lighter members. And I'll again use my pen tool for this. So if I click the pen tool on, and what I can do is actually just snap to the member. So I'll click that node and go up in the Y. And if it offsets there, it means my snap size is too large. So I'm just going to reduce the size, my snap size. So connecting from node 11, I'm going to connect to that member. Connect to there. Snap to that member there. So I'm just checking these are all connected. It looks like these 2 didn't really connect. So again, this might be too large of a snap size. We're dealing with quite a small structure. So I've got, in meters, you've got to be wary of that. So I'll just use the drag tool just to pin it back down to the member. And this one as well. And you can see it's linked up to the other one so it knows it's on the same axis. And same for this 15 as well. And I'll show you how we can confirm that they're connected once we look at the analysis. But I'll do this last member. And maybe we'll just brace this one across the top as well. Okay, so pretty happy with how that's all turned out. I can see that I've been applying green members, so section 2. See these vertical members are section 2. So I'm just going to click and drag between here. Missed that, let's do it again. And I can mass edit those. So if I go members, and I'm going to change them to section 1. I want them to be the lighter sections, the black sections, to keep the material weight down. And this one as well. Okay, so let's see if this structure holds up against the applied loads that we've added to this model. So I'm going to go ahead and solve again. And we're going to look out for the same results. So let's check deflection here. Now we can see it's deflecting in a whole nother shape. You can see more weight has been distributed across the span of this structure and less focused on this area here. It's because we've braced it and we've made it stronger in this region that it's going to be able to take some of that force. And I can see the max deflection, about 14 millimeters. That might be okay. Let's check the stresses under that weight. And I'll just confirm that my limit state is okay. 7, now we can still see it's failing. So we might have to increase the strength of the cross section. So let's quickly go back and make some minor adjustments here. And we can change the dimensions from here as well. So let's go to like an 8 mil. And that might be enough to strengthen it up. Checking the stress. Okay, so now we can see under that limit, the 7 MPa limit and my max and mins. It seems like the bending stresses are all okay. Shear stresses are fine. And my model seems to be safe under that load that we've applied and under the limit of 7 MPa for all of our members. So this would be a design that I would see as working. And so from here what I can do is actually get the material, the structure weight as well. So if I run an analysis report, and I can turn all of these off. I won't need any of these except for the bill of materials, so I can turn the nodal results off. And we'll turn on the load combination and we'll do it just a text file and we'll increase the precision to 6. So under those settings I'll create a report, and this will give me the bill of materials for each of the member types. So it'll tell me how many of each section I need and what length, but it'll also give me the total mass in kilograms. So I can use this number to check my weight of the structure, and once I've got a design that works, I can try and reduce the weight of the structure, and I can easily check what we are for that weight. So I can see here it's 0.075 kilograms. So there you have it. That's a design that would work, and I'm able to edit and try new things and modify my designs quite quickly using the software, rather than building it and breaking it and doing physical tests on it. So again, this offer is available. You can get access to this software just by visiting skyciv.com/Olympiad for $40 for 6 months. We hope you enjoyed the tutorial. We hope you found it very educational and helpful. You can also save your files and share them with your team. So if this is a design that you want to keep, you can save it as design 1. And everyone can have a go at sort of coming up with their own designs and seeing who can come up with the lightest, most efficient design using software rather than the physical experiments. So I hope you enjoyed the tutorial. Please feel free to leave your comments below if you have any questions. Otherwise, good luck with the competition and we hope to see you on board.